we'll get started. I'm sure other people will continue to join us in the coming minutes, but I'll give you a brief introduction. So Alex Moore, Ingrid Zabel, and I, Rob Ross, are part of the PRI climate team. Don Haas is on a well-deserved vacation today. Some of you may know of him. So we work together on a variety of kinds of climate change and critical zone science outreach initiatives, including teacher professional development. And this is the third in a series of 4 workshops about critical zone science. And so I will pass it to Alex to tell us about today's activities.
All right, welcome to all. The first thing is that you have an assignment. There are links to the agenda in the chat. And so if you don't have the agenda open, go ahead and open it up, in some space where you can access it while you're watching and participating in the workshop. Your first assignment is to introduce yourself in the chat. And we'd like you, in addition to saying where you are in your job title, we want to know what watershed you're in. And we have a link in the agenda. If you don't actually know that, you can figure it out. But please go ahead and tell us where you are in the world and in the world of watersheds. I'll tell you where I am. I work at PRI, which is in Ithaca, New York, and I live on the southern edge of the 6 Mile Creek watershed, which feeds the Finger Lakes and thus the Great Lakes and the St. Lawrence Seaway. If I walk south from my house about a mile, I actually cross a major watershed boundary, and I'm in the Susquehanna River watershed going down to the Chesapeake Bay. So it's kind of fun to live right on the edge like that. So go ahead and throw this all in the chat so we can see who you are and where you're from. And while you're doing that, I'm gonna get a PowerPoint going here. So let's.
And while you do that, I'll mention, I think I said who we were without actually saying where we work. Many of you may know. We are at an organization called the Paleontological Research Institution, which has an active earth and environmental science education program. And we are, at least in our local community, sometimes better known by the names of our public venues, which are the Museum of the Earth and the Cayuga Nature Center. But many of you are coming from other, maybe nearly all of you are coming from other parts of the country. And so we are an affiliate of Cornell University, but distinct. And we do outreach both in our local community and the kind of workshop that we're doing today.
Okay, and so this workshop is sponsored by the National Critical Zone Network. And some of you, I think, perhaps are old hands and you know what the critical zone is. But for those of you who are new to this, the critical zone is a way to define the outer skin of the Earth, the part of the Earth that we live in. So we typically define it as extending from above the tree canopy down through the solid Earth to the groundwater interface. And so when we are studying the critical zone, and a place where so many different things are going on, that requires that we bring a lot of different disciplinary expertise to that. So what sorts of disciplines do we draw on to study the critical zone? For example, engineering. If we're going to go deploy instrumentation in the field, there's got to be a lot of engineering behind that to get that stuff up and running. Clearly, there's a whole lot of physics in both the physical world itself and in the instruments that we bring to the study of that world. Under our feet, we have tons of geology, which is my favorite. That's my expertise. Of course, there's all kinds of chemistry that's happening as well. And then every different discipline within the biological sciences. And in order to make sense of all that, we apply the tools of math, the tools of computer science. We examine this through the lens of human history. And of course, we share that via language, math, and art. So this is a very engaging space to work in, and one where we can really bring all of our different expertises to bear on the subject. So today, we are talking about water in the critical zone. And this workshop is going to be divided up into 3 sections. So in the first part, we're going to be talking about watershed processes and exploring some different watersheds and what kinds of things might be important for those. The second section will be about not water, it'll be about drought. And then we'll wind up with a look at what confronts us as the ocean and sea level warm up and begin to rise. So those are our 3 sections, and I will get started with our watersheds. And let's start on square one and look at the USGS version of the hydrologic cycle. And when I look at this, to me, there are 3 really important processes that are going to be operating no matter where you are on the surface of the earth. We have evaporation of water out of the ocean, subsequent condensation and precipitation, either back into the ocean or onto the solid earth. And if that precip lands on the solid earth, then it has to run off and return to the ocean. Within those 3 sort of, I call them big parts of the hydrologic cycle, we have many other really important processes, and they're going to be more or less important depending on where you are. And so that's something that we'll think about as we go forward here over the next few minutes. So we also talk about cycles like this, either running in steady state or non-steady state. We hope that our hydrologic cycle is in steady state, where all of these processes are balanced, where the storage of water in these different reservoirs stays more or less the same. But unfortunately, in a world of changing climate, we know that we're not actually running in steady state now. We are losing some of our snow and ice reservoir and sending that back down to the ocean. Superimposed on those long-term global cycles, we have short-term extreme events. And we just saw a really good example, good or bad, example of this last week when we had extreme precipitation events in the US Midwest and resulting catastrophic flooding. And just to give you a sense, when we say extreme, here's this is actually a NASA product, the precipitation estimate for the period from July 25th to 31st. And in Eastern Kentucky, I've got the monthly mean precipitation over here in the lower right. And so you can see that the precip is fairly constant throughout the year, between 3 and 5 inches in each month. And so when the Jackson, Kentucky Met Office recorded 4 inches of rain on July 31st, that's a whole month worth of rain in 24 hours. And so that's an extreme event and obviously had some extreme consequences. And I don't want to show you pictures of an ongoing catastrophe. So what I'll do instead to sort of illustrate what that might look like is to jump back a year when we had a similar event here in Ithaca. Back in October, we got 3 inches of rain over a 24-hour period, and it made our creeks go nuts. Fortunately, nobody was hurt in this event. And in fact, most people ran down to the creeks with their cameras and took pictures. As I did with my drone here. So this is a creek that normally runs in October. It normally would run at a discharge of 40 cubic feet per second. That's the long-term average discharge. And on this day, it was running at 4,000 cubic feet per second. So one of the kind of basic things that I think we all understand intuitively about the hydrologic cycle in a terrestrial system is that when it rains, the creeks rise. And so we've seen plenty of recent examples of that. So when we look at that terrestrial system, superimposed and completely enmeshed with the hydrologic cycle, we've got Earth's climate zones. And so this is one way of looking at the climate variation across the terrestrial surfaces, the land surfaces, where we have this Köppen climate classification. And Ingrid, you can probably say it better. I don't know how you say the little umlauts over the O, but anyway, where we have 5 major climate zones: tropical, arid, temperate, continental, and polar. And within those 5 zones, the 3 middle ones, arid, temperate, and continental, are all modified by what the summer and winter temperatures are and whether or not there's strong precipitation asymmetry. So precip and temperature are used to modify those 5 major categories. And that's why you see all these different colors down here in the legend, particularly for the temperate and the continental categories. Where I am is right up here in the kind of baby blue in a continental climate. And I'd have to actually go look up what those modifiers are for this one. But anyway, so this is the climate system works hand in glove with the hydrologic system. They are in many ways inseparable from each other. And that's important. Because the climate is not only going to determine what sort of ecosystems we find on the surface of the earth, but it's also going to be really important in developing the landforms that we see on the earth's surface, and also what kind of resources we might have access to, we as human communities, but also natural communities. So having said that, let's sort of zoom in now and start to think about watersheds. So a watershed is any place that collects precipitation and sends it to a single point where it's going to enter back into the global ocean. Here, I'm showing you an example of the Mississippi River watershed in the continental US. And you can see that it is divided into some sub-watersheds. And then, of course, those are divided into smaller and smaller watersheds right down to the tiniest little creek. And we like to say everyone lives in a watershed. So when you're thinking about working with your students, I think watersheds are a really accessible topic because it's something that at some level everybody has access to. But then at the same time, while everybody has access, everybody is going to have access to a watershed that might look kind of different from other watersheds in other places. Because of this interlocking hydrologic and climate system. And so we want to think about what processes are important in each basin, and are they the same everywhere? Or are there some things that are different that are going to produce some pretty different results? And so, for instance, here just visually, are some things that you might see if you go across the country to some different sorts of watersheds. Most of these are natural watersheds, but you see I've included an urban one down on the bottom there. And clearly some of these are in places where there's a great deal more precipitation than others. And so with these things in mind, we're going to do our first activity. So what you're looking at here, I have 3 different hydrographs for you, and I've labeled them A, B, and C. Okay. For each hydrograph, I'll just point to B because it's away from all the little pictures on my screen. For each hydrograph, we have months of the year across the x-axis, so January to December. The left-hand vertical axis is discharge of a stream, and this is in cubic feet per second. The right-hand vertical axis is precipitation in inches, and both of these are the monthly means. So here where I've got precip in June at 5 inches, that's the monthly mean for June for this place. And similarly, the monthly mean stream runoff is 300 CFS. Okay, so that's watershed B there. So the precip is the pale curve in all of these graphs. The river discharge are the darker curves in all of these graphs. So we've got streams A, B, and C. And you can see that they behave kind of differently from each other. So what we're going to do is send you out to breakout rooms. And these are the questions that I want you to think about in your breakout room. Discuss this with your group. What do you think the characteristics are of this watershed? I'm not telling you anything about them other than what you see on the screen. You've got the mean monthly precip and you've got the mean monthly discharge of the stream. I will tell you these are all in the lower 48 US states. All right, they're not all over the world. What kind of hydrologic processes control the pattern of precip and river flow? What else could you infer about this watershed? And then make a guess about what stream you think this is, or at least where you think it is, or maybe point to a stream that you think probably looks a lot like each one of these, okay? And cite your reasoning. I guess when you go to breakout rooms, you're going to lose this graphic. So I actually put it, it's in the agenda. There's a link to it. I think it says link to watershed data graphic or something like that, so that you can pull that up and be looking at it while you're in your breakout group. Clear? Okay, Ingrid, can you send everybody off?
Yep,
And I think we'll break out for about 8 minutes.
that sounds good.
Okay, sweet. I'll see you all back here.
Okay. I still see a few of you here in the main room. Hopefully you have something on your screen that you can click to join your breakout room. And just a reminder, if you're sitting in this main room, this room is streaming live on YouTube.
So I'll just sit here with a frozen smile on my face.
Yeah.
Or be like Rob and turn the camera off.
Mhm. And Anthony and John, if you're there, we have gone into breakout groups. So if you'd like to join them, this would be the time. So we'll reconvene at 2:27. Is that about right?
Yeah,
Or 2:20, I think I had 2:26. I guess I'll.
Mhm.
it's
hit the-
fine. That just gives us more time to talk about it. It's fine.
Mhm.
Because I don't think under any circumstance there's enough time for everybody to report back. So how many rooms
Mhm.
were there, Ingrid?
I made 9 rooms
9. Okay.
so that there were about 3 or 4 people in each room.
Oh, okay. I can still hear the thunder here. Oh, my lights flickered.
I saw that. Wow.
That's interesting because mine did too, and I am. As
You're
you-
on the same power line as us.
Well, I'm at in Palmer.
Oh, you're in Palmer. Oh,
Yeah, so it
Huh.
must be. I mean, still, it must be the same power system.
Wow. Yeah, that's the
but
second
further
time.
apart.
Earlier this afternoon, they went off for like almost a minute, but came right back on.
Certainly looks really dark outside and threatening.
Well, we need the rain.
Yeah.
I know. How is it that the water is all just badly distributed?
Mhm.
Yeah, come on, people, get on this.
Mhm.
Then again, be careful what you ask for.
Mm.
Yeah.
Oh, I'm going to look at the chat while we're waiting for everybody. El
So, yeah, it
Paso,
occurred to
Rio
me that,
Grande.
this is not being recorded as a Zoom recording. So,
Can we
that means I'm not sure
capture?
if the chats are saved in the YouTube video. I think
They're
they are.
not, yeah,
Okay.
they're not, but we'll get a chat log when we exit the Zoom call.
Well,
But
even
if I'm looking at the chat and I'm sharing my screen, do you see that, or am I just looking at that?
We just see your main screen. We don't see the chat
Okay.
on your screen.
All
Yeah.
right. Oh, somebody from Colorado Springs. Well, then they should know the answer to one of these. Ooh, in fact, oh, Sabra, yeah, from Boulder. Look at all these mid-Atlantic people.
Mhm.
Yeah,
Yeah.
the Chesapeake Bay watershed.
Virginia. Yeah. Mhm.
All right, it's 2:25. I'm going to hit close all rooms, which I think gives people a 1-minute warning.
Okay. Do you think I should ask people to put their hands up or just chime in?
Just chime in.
Okay, yeah, I think so. Okay.
Yeah, I think it depends on how many people respond, but in these circumstances.
Are we all back?
I think everyone's back now. Yep.
Okay, all right. I hope you're all back. So what we're going to do is I'm going to ask you all to share, and we're just going to let you unmute and talk. But before you do that, I want to go stream by stream. So first, I want to talk about stream A. So if one of the groups wants to open it up and give us your thoughts on stream A, just identify yourself and go ahead and tell us what you think.
So we were, sorry,
No,
We
I was
were
gonna say,
in-
if you don't talk, I'll call on you, but go ahead.
we were in group 6, and we were noticing that there is a lot of precipitation, like in the winter months, and in the summer it was almost like it was drying out, and the precipitation and discharge kind of going hand in hand. So if there's a lot of precipitation, then there'll be a lot of discharge, and if there is not enough, if it's a low, like in the summer months, almost zero for precipitation. I was thinking maybe it's some kind of a desert environment, something like that. I'm not sure if I was right or not about that, but that was our idea.
Okay, that's excellent. This is clearly a watershed with really strong seasonality. Does another breakout group want to pick that up and maybe take it a little further?
So I was in group 1, and I actually live in the Sacramento River Valley. So this graph reminds me very, very much of home. So living in Northern California, our seasons are not rain. Around October, not snow. Around October, we start to get rain. And then around March, we stop to get rain, and we don't get rain for the rest of the year until we hit October again. So you see these really massive dips. And to me, this reminds me a lot of home, where you're seeing the drought and then the intense precipitation and that following pattern.
Okay, so here's building on that first idea of really strong seasonality, but maybe not necessarily a desert. Okay, someplace where there's just a really strong winter summer change in precip, but not necessarily leading to a desert ecosystem or desert vegetation. Anybody else want to add one more comment to this watershed? And then I'll tell you where it is. Anyone want to disagree with what was said?
Well, not necessarily disagreement. John from Group 1 is that just as an observation, the precipitation and the discharge they conform to each other almost perfectly, indicating that where it's occurring is an immediate discharge reaction. That's all.
Okay, yeah, for sure. There's a really strong correlation. So I think I'll advance the slide, and if we're lucky, this is Eel River, California. So Sacramento, you're all over it. And the things that you all described are exactly right. We've got a really strong seasonal signal. We have an enormous variation in precip from summer to winter, but not necessarily producing desert conditions, but certainly producing watersheds that respond immediately to what the rainfall is doing and march hand in hand with what the rainfall is doing. And also the vegetation is green year round. Okay, I hope I can go backwards. Yes. All right. Somebody tell us about River B.
I was in, I think, group 8. And this set of graphs looks much similar to what I show my students here in Western New York, where you've got a sort of delay between the precipitation and the discharge. I don't know if the discharge always gets quite that high, but this looks to me more of a reasonably humid climate, but sort of moderate with our seasonal increase in the spring of rain.
Okay, so there we see some seasonality here too, but different from what we saw in the first one. Somebody else want to jump in on B and take it a little further?
This is Jerry Corolla from Colorado Springs, Colorado, Fountain Creek watershed, and it also looks similar to ours, where we get snow melt and a lot of rain in the summer times, and then it dissipates October. So June, July is our high water flow.
Okay, excellent. One more person before I tell you where this is.
We were actually also talking about the fact that it might be a mountain kind of environment with the snow melting and adding to discharge of the stream. So kind of had that idea.
Okay. All right. Let's go find out. This is Boulder Creek, Colorado. All right. And I'm sorry, this photograph, for those of you who are in Boulder and Sabra, I know you're there. This is not actually Boulder Creek. It's a couple creeks north, but it's the best I could do for photos. So here, this hydrograph is dominated by snowmelt. Okay. For those of you in the Northeast, like Buffalo and like we are, we actually see a modified signal like this. So yeah, we do get a big snowmelt peak. For us, it's usually in April, not in June. But that same sort of input from snowmelt that is sort of decoupled from the ongoing precipitation is something that we see here. All right, let's go back and let's hear about River C. Yes, silence. I did save the hardest one for last.
Well, I guess I'll tell you what our group was talking about. We were talking about how the discharge is actually getting lower as precipitation increasing. We're thinking maybe the ground is becoming more, permeable, so the water can infiltrate versus just running off on the surface. One of the idea was in our group is that it was somewhere in Florida, maybe. Maybe it's a hurricane season or something like that. We weren't sure.
Okay, so yeah, you notice that there's a clear mismatch between the precip and the runoff. And in fact, at times of pretty high precipitation, the runoff is at its minimum. Amy, you got your hand up. What do you want to say?
I live in Northern Virginia and I hike year round. And in group 3, we were talking about how this could be somewhere in the Mid-East Coast. From one of our participants was in New Jersey, where the rainfall varies. But here in New Jersey, I mean, in Virginia, because I always photograph the waterfalls, we have heavy discharge in the winter and spring. And then right now, creeks that normally I can't pass through or I'm up to my knees in the water, right now I can walk through and not even get my shoes wet. Yet we're experiencing regular patterns of rain. And then we'll go through some dry times. So we are seeing fluctuation right now in our precipitation. While snow, I have not really seen much at all in Virginia the last 11 years. We do see some in parts. So my guess is that this is somewhere on the East Coast in the Virginia region.
Okay, let me see if anybody has an idea of what causes this really large mismatch in precip and runoff.
Alex, there's a comment in the chat. Says Timothy says looks like a dam possibly.
Oh, no. No dams. These are all at least to first approximation free flowing streams. I'm not tricking you. This isn't a trick question. All right, does it
something to do with the sedimentation of the infiltration versus the other graphs that we saw?
Okay, there's an interesting hypothesis. Anybody have any other hypotheses?
A similar hypothesis involving groundwater fluctuation, feeding streams.
Okay. Yeah. You're all dancing around the answer and you haven't hit on it yet. I'm going to go ahead since my time is about up. For those of you in the Mid-Atlantic, this is a deciduous forest in South Carolina. It's the Tiger River. And all of those green trees in the image are the culprit. They intercept the precipitation. They either take it immediately out of the groundwater or they don't even let it hit the ground. And they pump it right back into the atmosphere. And that's why you see, I didn't see who was speaking, describing hiking in Virginia, but that's exactly why you see what you do. Because in the summertime, the trees are leafed out, they're photosynthesizing, they're pumping water into the atmosphere, and they are stealing it from the rivers. And so you see this very, very anomalous looking precip and water flow mismatch. I love this example. I love using it with students because it is so strange. And yeah, it shows you the power of trees, and trees are crazy powerful organisms. So I'm going to stop sharing and hand it off to my colleague Ingrid.
All right, thank you. So I'm going to start by, well, so we're going to talk now about drought, and I'm going to start by asking you some questions. So I have here a liter of water, so it's 1,000 milliliters. And let's imagine that this represents all the water on Earth. So where do you think most of the water on Earth is? And you can type in the chat or you can just shout it out. Where is most of the water on Earth? In the ocean, Linda says. Yep, in the oceans, right. So here's 1,000 milliliters. How many milliliters of water do you think represents all the fresh water on Earth? Or you could think in a percentage if you want. Does anybody know?
1.
1, that's pretty close. Yep. And someone said 3, 2. Yep. So it's the answer is 3. It's about fresh water is about 3% of the water on Earth. So 3% of 1,000 milliliters is 30 milliliters. So I'm going to pour that off. Let's see if I can do that. That's about 30. I can pour salt into the rest. Okay, so here's the ocean, all that salt water. I'm going to put that away. Okay, so here's my 30 milliliters roughly of that represents all the fresh water on Earth. So now let's think about where that is. Think about the polar regions, so the Arctic and the Antarctic. So what is a lot of the water, the fresh water there, and what form is it? Glaciers, ice.
Ice.
Yep, frozen, exactly. So it turns out that about 80% of all the fresh water on Earth is frozen, mostly in the Antarctic ice sheet and the Greenland ice sheet. So those massive ice sheets that cover Antarctica and Greenland, but also in some mountain glaciers. Okay, so here's all that fresh water, but a lot of it is frozen. 80% is frozen. So I'm going to pour off into here 20%, that is fresh water that is not frozen. So 20% of this would be 6 milliliters. Let's see, this is one of those little medicine spoons I used to use with my kids when they were little. See if I can get 6 milliliters. Yeah, it's a little high, but maybe close enough. Try to pour a little back. Okay, close enough. So this is all the non-frozen fresh water in the world. So that's water on the surface. It's water underground. Now, how much of this liquid fresh water is usable to us? So usable means not polluted, not so deep that we effectively can't get it. So to represent that, I wish I had an eyedropper, but I just have this sort of metal tube. And I'm gonna dip it in here and just get out 1 drop and put it into a cup. There. So you probably can't see this on my screen. It would be more effective in your classroom, but here's my cup. And there's 1 tiny little drop of water in it that I took out of that medicine spoon. So that represents all the liquid fresh water in the world that's usable to us relative to a liter of water being all the water in the world. So I would hope that if you showed something like this to your students, they would get some sense of the fact that water is really precious to us. And I'm going to share my screen now. Okay. So there's not that much, a very small proportion of the world's fresh water that's usable to us. So we need to conserve water. We need to not pollute it. And we need to keep salt water out of freshwater systems, ecosystems, and aquifers. And climate change makes some of those things harder. So let's talk about what's going on now with drought and climate change. So this is a map that was actually released today, but it's showing data for the last week of the state of drought in the US and its territories. And you see it's not looking good. I mean, of course, really severe or extreme or exceptional drought in the West, in the South Central region, but other parts of the country, including where we are here in Central New York, we're also having abnormally dry weather or some moderate drought. And you see it elsewhere, Hawaii, parts of Alaska, Puerto Rico. So this has not been a good year for drought. And in the West, this has been a long-term drought. I heard a talk by a climate scientist who said that he feels that drought in the West is permanent. I'm not sure everyone would agree with that, but it's a pretty dire assessment. And this is from, by the way, from the US Drought Monitor, which is a wonderful site. There's so many different maps and mapping tools that you can play around with. So I'll encourage you to look at that on your own time. And there's a link in the chat. So how do we define drought? 4 years ago, when the latest National Climate Assessment came out, I attended another webinar by a meteorologist, and he talked about different types of drought. And at that point, I had no idea. I just thought, well, drought is drought. But it turns out that scientists define many different types of drought. And on drought.gov, if you go to this website where this graphic came from, I'll read you this quote. It says, in the early 1980s, researchers found more than 150 published definitions of drought, reflecting differences in regions, needs, and approaches. So, there are a lot of different ways to think about drought, but these 5 are kind of the major categories that scientists think about drought today. So one is meteorological drought, and I think of that usually as simply lack of rainfall or lack of snow. And that kind of drought can start very quickly and can end very quickly then if you get a lot of rain again. Then there's hydrological drought. So this is when you have low water in systems like streams and reservoirs, and lake levels go down and groundwater levels are low. And that typically happens a long time, maybe many months after you have lack of rainfall. So following meteorological drought, and can take a longer time to recover. Then there's agricultural drought. So this is when crops become affected. And again, that could be from lots of different things. Could be lack of rainfall, dry soil, reduced groundwater, or low reservoirs, the reservoirs that are being used for irrigating crops. And I'll just mention that here in New York State, we have had in the past 50 years increasing rainfall. So our total rainfall in New York State has been going up, but projections for the future, say for the end of this century, are that we're going to get more drought, sort of short-term late summer drought, not because rainfall is going down, that's projected to continue going up, but because the air temperatures are going to be so much higher that there's more evaporation, and that evaporation will outweigh the extra rainfall. So we are projected to not have meteorological drought, but to have agricultural drought here, or more of it at the end of this century because of climate change. And then there's socioeconomic drought. So when drought impacts supply and demand of goods, produce and grains and commodities like that, or it could also affect things like power. For instance, if there's not enough water to run hydropower plants or to cool other types of thermal power plants. And then ecological drought, when natural systems are affected. So lots of different types of drought. So how is climate change affecting drought? Because we've always had drought, or even before there were human beings in the world, right? There have been dry times and not so dry times. So what is the effect of climate change today? Well, there are different things going on. So one is, if we have higher summer temperatures, that's leading to faster evaporation, that's drying out the soil. So that's one type of drought we're experiencing. Then we're also getting higher winter temperatures. And here in the Northeast, that's the season where temperatures have gone up the most in the past 50 to 70 years. So that can lead to decreased snowfall. So we're getting maybe more rain in the winter, or precipitation that used to be falling as snow. And so we're getting less water from snow melt. And you might say, well, what's the big deal? If you're still getting a lot of precipitation, why does it matter if it falls as rain or snow? Well, it matters because when you have snow melt, that melting occurs gradually at the end of winter, and it's sort of hydrating the soils and hydrating the plants over many months. Like, for instance, Alex mentioned from Colorado that the discharge was highest in June, I think you said. So that's an advantage for agriculture, right? That you have this nice gradual release of water into your systems. All right, what about higher spring temperatures? So it's also related to snow melt. Then you can have more rapid spring snow melt, and then you have a shorter time period where, again, you have that hydration from the snow melt. And then finally, climate changes globally are changing precipitation patterns geographically. So storms are shifting. The boundaries between dry and wet regions are shifting. And I'll show you one graphic. This is from a really nice article from the Yale Environment 360 project. This was, here you see two graphs. It says 1980 and today. Today was 2018. That's when the article was published. And there's this divide in the contiguous US between dry and wetter regions, and that has shifted east over the past few decades. And so you can imagine if you lived in this region along the boundary, previously in the wet region, but now it's shifting towards dry, that could have profound effects on agriculture and on the water supply in those regions, and the way that people have traditionally done things may not work anymore. And if you go to this website, there are lots of other really nice graphics where you can see shifts in temperature and precipitation zones. All right, so I just wanted to briefly tell you about some nice teaching resources that I found for teaching about drought. So one is from CERC at Carleton. They have a whole unit about drought, and they have a nice simple experiment on soil moisture. So you could take 2 containers and fill them with soil, and one keep dry and one make wet. So you add some liquid to it, you cover them with plastic, tighten them, and then just leave them out in the sun for a short time and see what happens. And you might expect to see some condensation on the plastic. So, and they have an extension for this, where if you have some soil moisture probes, you can actually make some measurements of soil moisture over a longer time and make some predictions about how the two will differ. But I think this is just a really nice illustration of evaporation and the effect on soil moisture and how that has such a direct effect. And then you can connect the dots for students on how that would impact agriculture, for instance. I also wanted to mention Project WET. So they have some really nice activities. And in fact, that one I showed you at the beginning with a liter of water comes from one of their activity sheets. And in that one, they have an extension where after you've done that demonstration, and so students can appreciate how small a proportion of usable fresh water we have in the world, then they have some hands-on exercises and almost like games where students have to figure out how to share that water and distribute it equitably. And I think that's a really good learning tool. So if you go here, it'll look like a store, and there are a few things you have to pay for, but a lot of things are free, like this one you can download for free. I also want to mention on PBS learning media, I think it's really important when you're teaching climate science to also contextualize it and talk about the impacts on people and combine those, both the basic science and the impacts. And so they have 3 really nice videos about the impacts of drought on people, 2 in the US and 1 in South Africa. I'm not going to play one of these because they're each 9 minutes long. but they're really excellent, and they bring in social justice issues too, which I think are important in teaching about climate change. So I highly recommend these. And then back to Project WET, one of the really nice activities that they have in those downloadable resources is a school water audit. So some of you, if you've taught about climate change before, you may have done energy audits in your school, or at least thought about doing an energy audit, but you can also do a water audit and see how water is used in the classrooms, in the kitchens, in bathrooms, in schools, all different parts of schools, and they will guide you through it. I know this is impossible to read at this scale, but they'll guide you through, and they have data sheets where students can measure and quantify the water use. And then they have lots of great links for sources to learn how to conserve water, so that after the audit, you can come up with ideas for how to change and do better. And I guess I will just finish by, that's all I had to present, but I thought I'd ask all of you, if you have taught about drought in your classroom, how have you found some effective ways to get students to understand the impacts, to understand the science, or, what have you done in teaching about drought that you think has worked well? So I'm going to stop sharing, and if anybody wants to share in the chat or just speak up, we'd love to hear from you.
Several years ago, John Cunningham, several years ago, I introduced my students to a book called The Pillar of Salt. Incredibly, very frightening, actually. We had to calm ourselves down about halfway through the book. It turns out that all irrigational cultures eventually saltate the soil. It's all of it. It's not some of it. And I asked them to come up with ideas about what to do, and looking at the recent history of saltation, especially in India and places like East Africa. And they did the reading inside and outside the book, and there were makeups that didn't stop the saltation process, but because we're in the genetic era, a lot of their ideas had to do with the modification of some of the agricultural products to deal with extra salt in their ordinary everyday water. So it's that was where most of my students went to, aside from being scared that it's going to happen to all of us soon. But Pillar of Salt was quite a experience for everybody.
Yeah, that sounds pretty a dramatic illustration of a geological process, I guess, or geological and hydrological. Thank you. Anybody else have something to share? Oh, and there was a question in the chat. Are the resources or slides shown available for sharing? So yes, in the agenda, there's a link to the slides, and I also put in the links to many of the resources that I showed.
Yeah, and I relinked the agenda in the chat if anyone came in late enough and didn't see that originally. I think if other people want to share resources in the chat, that would be great. And I think we'll keep moving along to part 3 of the workshop, where we're going to talk about sea level rise. And that means I get to share my screen again. Okay, so you should be looking at a bunch of taxis. So this last part about sea level rise is about when you have too much water and the wrong kind in places where you don't want it. And this is an image from Hurricane Sandy in 2013. So what I want to talk about is the thermal expansion of seawater and the contribution of that to sea level rise. And I actually was going to do something else in this third part until Tuesday of this week, when I actually got to go to a ghost forest in the Mid-Atlantic coastal region. The Critical Zone Network that is sponsoring these workshops consists of 8 groups that study different aspects of the critical zone, and the Coastal CZ Network hosted a meeting, an all-hands meeting for everyone who's connected to CZ Science, and I was privileged enough to be able to attend and take a field trip to the Delaware coast, where one of the research sites is, and where there is a developing ghost forest. What you're seeing in the background of this slide, this is a NOAA website where they've got all of the tidal gauges all over the world actually displayed in real time. And you can see, it's pretty clear from this image that sea level is rising everywhere. And a really good resource to understand sea level, both generally and in a lot of detail, is the Intergovernmental Panel on Climate Change. And a couple of years back, they put out a special report on the ocean and the cryosphere. And the link is down here and also in the agenda, I think, and if it's not, I'll fix that. But when we think about sea level rise, there are two processes that are responsible to this. And the one that most people talk about all the time is melting of continental ice sheets and mountain glaciers, because that's where we have a lot of the Earth's water stored in a continental reservoir that is now being transferred to the ocean. And so that contributes to sea level rise. But the other thing that contributes to sea level rise is the physical expansion of the warming ocean. And right now, those two processes are both contributing about equally to the sea level rise that we've observed already. I'll circle back around to that in just a minute, several minutes. But this graph, the graphic on this slide, comes from that IPCC report. And one of the things that's important to understand is that even though right now sea level rise is in millimeters per year, which seems like a small number, but the problem is even those very small sea level changes contribute to the frequency with which extreme events affect us. And so what this graphic is trying to show you, there's no scale on either the X or the Y axis, but we've got, recent, past, and future, and then these different sort of extreme events. Something, if this is meant to be the continent, the little gray part, and here's mean sea level now. If sea level goes up even a little bit, an event that might happen in the past at a frequency about once a month becomes much more frequent. And so, for example, if we go up to the top of this graph and look at what we would have called a once in a century event, we're going to be seeing those every year. So it's not only the overall change in sea level, but it's the way that makes these extreme events become more frequent. So on Tuesday, I was in Delaware. And so all you mid-Atlantic people, I was right down in your part of the world, looking at the field research stations for the Coastal Critical Zone Network. And there are 6 different institutions that are collaborating on this project. And a lot of the slides that I'm going to show you were very generously given to me by Holly Michael at University of Delaware. And they're looking at 3 different sites on the Delmarva Peninsula from north to south, up here in Delaware, in Maryland, and down in Virginia. And these are places that are profoundly affected by changes in sea level because the topography is very low-lying, because these are places where sea level is changing very quickly relative to other places on Earth. They experience frequent coastal storms, and we're seeing really rapid ecological change in these areas. And that's what this first graph is. This is a normalized difference vegetation index, which tells you about the changes that we're seeing in vegetation. So the places that are in red and orange are places where vegetation is being lost, and the places mapped in green are places where the vegetative community is changing from one type to another. And then on the right, everything in orange is 5 meters or below with respect to sea level. So already the work that these groups are doing have come up with some pretty dramatic results. And so, for example, there are places in the Mid-Atlantic region where we're seeing forest and coastal retreat at a rate of up to 30 meters per year. So that's just astonishingly fast. So let's go take a walk through the coastal marsh and see what these sites actually look like. The vegetation that I'm pushing through here is an invasive reed. It's called Phragmites australis. And so this is a species that doesn't belong here, but it's one that's seeing expansion as sea level comes up. Okay, so we go through the Phragmites, we come out to the marsh, And we'll jump ahead. And so this is a very small incipient ghost forest. You see the dead trees along the edge of the forest where it meets. There's the Phragmites, and then this is a native reed that fills in the rest of the marsh. And so because sea level is rising, these forest edges are experiencing salt influx into the groundwater, into the root system. And so the critical zone researchers have installed a transect of instruments at 4 different sites from healthy forest all the way down into the marsh. And they look at a variety of parameters and monitor them continuously and in real time. Most of these instruments make measurements every 15 minutes. And so there's a really robust and rich data set that explains not only what's happening, but also helps us understand why. And so, for instance, I'm going to show you one of these sap flux sensors, and we're going to listen to one of the researchers talk about that.
What I've been working on here at Milford Neck is we have these sap flux sensors you may have heard about in Karen's presentation yesterday. If you remember, the way they work is they have these 3 prongs, where the middle prong is a heater and the top and bottom prongs are thermometers, basically. So if you send out a quick heat pulse from this heater and you measure how long it takes for the pulse to reach one of the thermometers, you can get a good idea, given some parameters about a tree like this loblolly.
Alex, we can't quite hear.
How fast and what direction.
I don't know that I can do much about that.
Is it possible to reshare, like click the video? Like there's a link at the bottom about sharing video and audio.
I did.
Oh.
That's all right. I'll come back to it.
Thing we've been working on is what you heard in Karen's presentation yesterday, where in a saltwater inundation, our measurements indicate that the flow rates can briefly go negative, indicating that perhaps the osmotic demand for water in the soil is so high that it's like sucking water back down out of the tree, which appears to have sort of a temporary but a solidly negative effect on the ability of the tree to transpire water positively moving forward in the weeks after that event.
All right. So I tried to make the audio on that clip as high as I could. I don't know if y'all could hear that, but what he ended up saying was that these the sap flow sensors that they put in the trees, when they have stormwater inundation events, the sap in the tree the sap flow is negative, meaning it's being sucked back down out of the tree. And what he said is the osmotic demand in the soil is pulling that water out of the tree. And if you say, wait, what? Think about what osmosis is, okay? When you have a semi-permeable membrane like the roots in the trees are, there's going to be a concentration gradient of salt and fresh water, and the freshwater potential is greater and is going to be pulled towards that salty solution. All right, and that's what osmosis is doing for us here. And as Riley said, what was the word he used? I can't remember. He said, but it has a very negative impact on the tree. Okay, so when that saline groundwater is pulling the fresh water out of the tree, that's a serious health impact that is damaging that tree and leading eventually to its death. Now, there are places further down the coast where these processes have been studied over a longer period of time, and where we also have really nice Google Earth imagery over 35 years. And this is one of them. This is the Alligator River National Wildlife Refuge in North Carolina. This whole peninsula here is the refuge. There are crazy cool animals that live here, including the endangered red wolf, as well as beautiful other plant communities and unique ecosystems. And what I'm going to show you, look along the coastline, and you see where there's kind of this brown zone. That's the marsh, and the edge of the forest is, where the green touches the brown. And so just in this section here, I've drawn a line where that zone was in 1985. All right. If we go forward, this is 2020. All right. And you can see that the brown has surpassed that original boundary in some places by more than a mile. All right. And I'm going to rock it back and forth so you can see that change a little bit better. Notice also, look at actually the coastline right down here too. All right, you can see that the coastline is retreating, the forest is retreating. You can actually also see up here, there's a whole bunch more living on that island. So this is a place where things are changing really, really fast. In addition to looking at natural ecosystems like the forest, the CZ team is studying agricultural sites, and we see the same thing. This is a farm, and this has been instrumented in the same way that the forest has. And you can see as we pan to the left that the corn starts to look unhappy. And then we have this zone where there's just grass, where the farmer has stopped planting entirely because his corn doesn't grow there. And then you can see the Phragmites, the invasive reed, in the background there. So this farmland is being abandoned because of saltwater incursion. And so in addition to natural communities, we have disruption to human communities and agriculture. So what I want to do, I talked about the two different reasons that sea level is rising, both from melting of ice and also from thermal expansion. It turns out that thermal expansion is really, really accessible to students. You can measure this very simply, and students can get a really robust answer to understand how this works and the contribution to sea level rise. And I'm going to show you a short video clip. I'm going to show you the first half of the video clip, and then I'm going to give you an assignment before we watch the end of it. So this is looking at how to actually measure thermal expansion.
Hey, welcome to the greenhouse. I'm Alex. Let's go someplace completely different today. Let's go to Paris. Did you know that the Eiffel Tower is taller in the summer than in the winter? Its height changes by 6 inches due to thermal expansion of its iron structure. Most materials experience thermal expansion, like the juice in this bottle or the water in the ocean. Thermal expansion is the property that makes a thermometer like this one work. There's a reservoir full of alcohol connected to a very thin tube. When the temperature increases, the alcohol expands, forcing the liquid into the tube. The increase in volume is proportional to the amount of liquid and to the change in temperature. The constant of proportionality is called the coefficient of thermal expansion, which we label with the Greek letter beta. The coefficient of thermal expansion is the fractional change in volume of a material with each degree of temperature change. We can use the soda bottle to actually measure the coefficient of thermal expansion. But since the volume change will be bigger with a bigger starting volume, I'm going to use the wine bottle for this demo. A wine bottle holds 750 milliliters, so I'll use a graduated cylinder and I'll fill the bottle up. All right, we're going to measure the temperature. We could do it with this thermometer, but I'm going to use a thermometer that you put in an aquarium. To get our starting temperature, and I'm also going to mark the starting level on the bottle. We're going to put this into a beaker on a hot plate. A pot on a stove would work too. And I'm going to set my thermometer here so we can watch it warm up. This prevents the bottle from breaking when we set it on the burner to heat up. We want to take it to about 50 degrees warmer than it is now. Okay, here's our final temperature. We subtract the initial temperature from the final to find the temperature difference, which is 54.3 degrees Celsius. So, now we've got to figure out what the change in volume is. And you can probably imagine a couple different ways to do this. What I'm going to do is I've taken the hot water and dumped it out, and I've refilled the bottle to the original mark with cold water. And I have a graduated cylinder here filled with 50 milliliters of cold water. And what I'm going to do is very carefully pour this in until it gets to the second mark. There we go. Now I can subtract the new reading in the graduated cylinder, which looks like 33, from my 50 milliliters that I started with for a difference of 17. And that's what our change in volume is. Okay, here are the three things that we know. The volume change is 17 milliliters. The starting volume was 750 milliliters. The temperature change is 54.3 degrees Celsius. And here's our equation. To find the coefficient of thermal expansion, we need to do a little algebra and rearrange, and then plug in our numbers. And we get a coefficient of thermal expansion of 0.00042 per degrees Celsius. Now, let's go back to the original equation, where the change in volume is equal to the coefficient of thermal expansion times the original volume times the change in temperature. We heated the water in the bottle through quite a large change in temperature, and we measured the change in volume, and we got the coefficient of thermal expansion mathematically. So what this means is that the volume expands with each little increase in temperature, and the size of the container also determines how much the volume changes. So we've calculated the coefficient of thermal expansion for water in this experiment, and the question is now, what do we do with it? The wine bottle has a pretty small volume when you're thinking about all the water in the world, right? But what if we use that coefficient of thermal expansion in a different situation, where we had quite a large volume of water, but maybe a smaller temperature change? Then we could calculate the change in volume for something we care more about than water in a wine bottle. How about the water in the ocean? Let's take a look at that. If we're going to apply our coefficient of thermal expansion to different situations, there's one thing we need to realize, and that's that the coefficient of thermal expansion is not constant. It's not constant between different materials. The iron in the Eiffel Tower is going to expand differently from the water in the bottle, and that fresh water is going to expand differently than the salt water in the ocean. And the temperature range that we're working with and the pressure range that we're working with are all going to influence expansion. But that's okay, because this is such an important parameter that engineers have done lots of experiments, and we understand the coefficient of thermal expansion really well. So let's apply a thermal expansion calculation to the ocean. Okay, for the ocean, we're going to calculate the change in volume for a particular temperature change. For this example, I've chosen 0.2 of a degree Celsius. We also need to know the volume of the water in the ocean, which we can look up.
Okay, I'm going to stop it there because I'm actually going to ask you to do this. Okay, so get out pencil, paper, spreadsheet, calculator, phone, something, and see if you can figure out from the numbers that are on your screen what the change in sea level would be for a temperature change of 0.2 degrees Celsius, for a coefficient of thermal expansion of 0.00017. And then here's your data for volume of the ocean and area of the ocean. I'm going to give you 2 minutes, maybe 1 minute. You can either shout the answer out or put it in the chat. And don't worry, I'm going to show you the answer in a minute too. Ingrid, we need some game show music while people are thinking, right?
Definitely. Do, 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 do.
It's always that song, isn't it?
I'll be right back.
got one answer that says it's not equal to 0. Okay, good. All right, I'm going to keep playing the video since I want to keep us on time here, but you can keep on working and I'm going to solve it for you in the video as we go forward.
4 times 10 to the 18th cubic meters. And we'll use a coefficient of thermal expansion that's appropriate for cold seawater, 0.00017 per degree C. Calculating the change in volume just involves plugging these numbers into our equation, and we've got our answer here, 4.76 times 10 to the 13th cubic meters. A much more interesting calculation would be to find the amount that sea level would rise because of this change in volume. To find that, we know that volume equals area times height, so height is volume divided by area, and we can find the amount of sea level rise, 0.13 meters, 13 centimeters, about 5 inches. So the math and physics of seawater tells us that if you warm the ocean, sea level will go up. There's no escaping this conclusion. Now let's put this number in context. One way to do that would be to find the sea level rise due to thermal expansion for some other temperature changes. And then we could look at projections made by climate scientists that arise from a warming ocean. So here we've got 0.3 degrees C and 0.4 degrees C, and the rise from thermal expansion for each of those. It's important to realize that if we warm the ocean like this, we're also warming the continents. And any ice stored in continental glaciers and ice sheets is going to start melting as the climate warms. So the amount of projected sea level rise is going to be partly from the thermal expansion of ocean water and the rest from melting glaciers, with thermal expansion causing just under half of the increase. These are projections from the Intergovernmental Panel on Climate Change for sea level rise by the year 2100. You can see that they range from about 1.3 to 2 feet. The basic material properties of water are defined by equations, and those equations allow us to ask questions about the future and to make projections. But is there any way to test those projections? The answer is yes. The physics of water is the same in the past, the present, and the future. So we can look at the past that we've already observed and see if that pattern fits our projection for the future. For example, we know that glaciers are melting. Here's a glacier in Switzerland, and marks on the valley wall show us where the ice used to be before it melted and flowed to the ocean. We can also look at records of sea level over the last 100 years. There are tide gauges that monitor sea level all over the world. These are the current measurements on the east coast of North America. Note that they're all going up. Let's go to Washington, D.C. The tide gauge here, near the tidal basin and the memorial to Thomas Jefferson, tells us that sea level is rising just over 3 millimeters per year. We can also look at the measurements of past records made at this station. We see that sea level has risen a little more than 1 foot in 100 years. And while 1 foot may not seem like a large amount, it's enough to have a serious impact on Washington's waterfront monuments. This 1 foot rise in sea level now floods the paths and benches around the tidal basin at high tide, twice a day, every day. So think about what we've just done. Thermal expansion is easy to measure in a soda bottle in your kitchen, but it's important for people who live in coastal communities all over the world. So understanding the process of thermal expansion is really important. It's important as we plan our response for problems now, and it's even more important when we plan our response for the future.
All right. So that's an activity that is presented as a video on YouTube that is linked to the agenda, so that if you want to go actually try it yourself, you can, and it's meant to be done with the simplest possible tools. So even if you don't have access to a science lab, if you're still working remotely or in any situation where you might be working remotely, you can do that. I think, Ingrid, what is next on our agenda here?
I think it was basically ending in the feedback form. But I wanted to mention one thing too in connection with the section. At the beginning of the video, Alex showed the alcohol thermometer. And one thing I love about the activity she just shows is how it quantified effective thermal expansion on sea level rise. But if you want something qualitative that's really quick too, you can take an alcohol thermometer if you have one in your classroom. And I don't know if you can see it here, and you can just have your students fold their fingers against the bulb, and their body heat, the heat from their finger, will make that thermometer rise. You can see that idea of thermal expansion just very quickly. So I just want to add that. It's kind of a fun and quick thing, not quantitative, but qualitative. But yeah, I think we have a feedback form, so we would love to get your feedback, and maybe we'll just, you can find it in the agenda. If you could just click on that and fill out that exit survey now, and then we will stick around and can take more questions after that.
Yeah, if anyone has questions, we're happy to keep talking.
And I have just posted the feedback form into the chat, which is also linked to from the agenda. And I do want to point out that Alex has a string of really great videos on the PRI YouTube channel. So we hope that you might visit some of the others there, all relating in one way or another to climate change and the critical zone.
I can put a link to that playlist in the chat.
And somebody asks about the links from this professional development. I think they're all in the agenda. So if you have access to the agenda for today's workshop, then you have the links that were mentioned over the course of the workshop. And if you have any further questions, please feel free to email us. Our emails are also in the agenda. We'd love to hear from you. The next workshop and the last in the series is on August 11th. That one I'm looking for the official title of it.
I think it's called Climate Change in the Critical Zone.
Yes, simple as that. So you'll hear some of the same themes, but as you know, climate change is a very interdisciplinary topic, so we'll address a wide range of issues.
I was going to say, we'd have to do a lot of workshops for me to run out of demos.
So I think we've had a few minutes now to work on the exit survey, but please continue working on it if you are. But in the 5 minutes we have left, are there any questions about anything you've seen or heard today?
Or comments or stuff to share?
Mm-hmm.
And of course, we want to thank you for joining us on a summer day. We know you're busy and there are lots of things that you could be doing. We're glad that you joined us today.
Of course, the three of us are stuck inside watching it rain out. It got kind of fierce there, Ingrid, while you were talking.
But we're very thankful for that rain because it has been incredibly dry here in this part of New York State. I'm curious if there are those of you who live
Rob,
in...
there's a question about certificate of completion.
Yeah, so everyone who attended today will automatically get a certificate of attendance from Don Haas, who is the fourth team member who he didn't join us today, but he did help organize this, and he will look over the people who attended today and send out a certificate of participation, I think probably within the next week. He will be back in the office probably by Tuesday. He potentially has jury duty next week. So if you don't get something right away, it may be because he has jury duty. But he will be sending that out certainly within the next couple of weeks. And if you have any questions at all, just shoot us an email.
And I think the question also asked about a certificate for the previous session. I know there was some issue with the email that was supposed to have gone out about a certificate for that previous session. And I think
I see.
He's on it now, but I'm putting his email in the chat. So if you were in the previous session and you didn't get your certificate or you still have questions about it, please email Don.
Yeah, thank you. I didn't notice that bit.
And also, I see a question about elementary school students. DeJean, why don't you email me and Ingrid, and we can maybe offline work with you to help get some things for younger learners.
Just a quick question for anybody that could answer it. I'm kind of fascinated with the role of combustion released water mostly from fossil fuels, whether they're coal, jet fuel, home heating, cars. Is there a reasonably accessible research that you know of that can put me in touch with what might be changes in volume of that water in the atmosphere as different times have passed over the past 100 years? Has anyone done any of that research quantitatively about the addition of water from combustion, which is not water that has already been there? It's brand new water, or at least water that hasn't been around for so many millions of years.
Mm-hmm.
Is there any place I can find research done on that, or data that I could use to do my own?
Ingrid, do you know anything about that?
No, I don't know, but if I were going to look, I would look to the IPCC reports and to the Scripps Atmospheric Monitoring Program. So for instance, in both those places, I know you can find data on oxygen in the atmosphere, and there's a measurable signal that oxygen, and here we're talking about O2 molecules, the kind that we breathe, has been depleted in the atmosphere as we've been burning fossil fuels, because if we know, of course, it takes oxygen to burn something. And it's not something to be worried about, like we're not going to suffocate because the oxygen is being depleted in the atmosphere. It's very small, but it's measurable. So I wouldn't be surprised if maybe water is measurable also, though at the same time, water moves so quickly in and out of the atmosphere that might make it harder.
Yeah, the
But those are the
natural
two
range.
places.
Yeah, those are great resources. And the natural range of water vapor in the atmosphere is huge. And so I'm not sure that it's possible to pick that signal out of the noise, but Scripps would be a great place to look.
I think that one possibility, however, is that it would probably be possible to make some back of the envelope calculations of how much fossil fuels have been burned, and stoichiometrically then how much water would be released, and then compare that amount of water to the reservoirs, for example, that Ingrid talked about. And so that's water depending on the water cycle, a substantial fraction of that might end up in the ocean. So in other words, we might not see it as like additional fresh water to the system, but it's an interesting question.
That's great. I have stuff I can get on transposition of data, knowing the formula for combustion, there's so much oxygen change and so on and so forth. And you can look at averages and just come up with general ideas despite the tremendous fluctuation. Thanks a lot for that information. That's great. Thanks.
I see a question about water in other countries, and I don't know of like a one-stop shop, but again, the place I would go first is to the UN, and I put a link in the chat to the UN Environmental Program. I suspect that pretty much every country is going to have their own sort of network, like we have the US Geological Survey to monitor water in the US, and I know in France they have an equivalent, and I'm pretty sure the UK Met Office does this. But if you want to look at sort of everything all at once, I would start at the UN. There's also a group called Our World in Data, and they have tons of different all kinds of data.
And very, really excellent visualizations of data. So it's easy to interpret.
I'll see if I can get that up.
Any other questions?
It's called ourworldindata.org. There we are. Oh, that wasn't it. That was my search result. Come now.
Thank you to everybody for joining us.
Yeah, thanks. Have a great summer. Or for some of you, summer's probably about to end and you're about to go back to school.
Linda doesn't want to hear that, I guess.
Sorry. All right. Bye all.